And here comes the thermal properties, chapter 19 in your book, William D.Callister. Well, we're done with mechanical properties, done with electrical properties, done with optical properties. And now we're talking about thermal properties. In the upcoming lectures, we'll be talking about magnetic properties and we'll be done with all properties. Thermal properties are very extremely important too. So here I'm going to talk about in the next few slides what kind of application areas we can use what we're going to learn in the scope of this lectures. So, for example, on the top left, on your motherboard, there are multiple components that are attached to a PCB circuitry, right? And each time you do some kind of process in between them on that circuitry, what happens? There is a heat comes off. So if that heat is not removed correctly, then this operation stops. So you need to have a heat sink to remove the heat properly from the area where these processes are established on a motherboard, for example, or some kind of PCB board where there are many electrical circuitry elements are present. So these finger pattern or plate-like heat sinks, there are many different designs goes into it. The aspect ratio, how deep they are, what kind of material are used there is an important concern. Or for a transistor, high electron mobility transistor, for example, we've seen it in electrical properties. There is in between the source and drain, there is an information process with the gate modulation, right? So based on how fast these processes are occurring, the electrons or the carriers doing the job create local heating in the system. So if this heat is not removed, what's going to happen, especially for extrinsically doped semiconductors, the operation will stop. So we need to have an immediate heat sink right after the chip itself to remove the heat. Or, for example, these has to do with, of course, the heat removal, but what about the thermal expansion? If I bonded my chip, the semiconductor chip on top of a board, let's say it's doing a good heat sink job, but let's say the thermal expansion coefficient is not as good, so which means they're not compatible. If the chip, as you increase the temperature, expands a little bit while the board expands a lot more, or when you cool it down, the board or the sink at the bottom shrinks more and your chip shrinks less. So what happens? On the chip you either have a tensile or compressive stresses, which eventually might crack your chip, making everything inoperational. So you have to pick your material wisely. Here, on the other hand, processing thermally is important. If you have a certain, maybe you remember back in 2007, the first smartphones came up, the iPhone 1. Once you dropped the phone, it was breaking, right? And in time, I think Corning in United States, they improved the screen properties, the touch screen properties, to prevent to make it harder to break, indeed, right? So the idea behind it is really similar to the tempered glass that we use in our homes, the large glasses that we use in our homes. That tempering is got to do with the thermal properties as well. Or playing with the microstructure of the material, depending on the size of the material piece that you're using. If you do some kind of thermal treatment, like heat treatment, and let's say you cool it down, sometimes if you pick a large piece, the outside will cool faster than the inside, so you're going to have a different crystal structure. If you pick a smaller piece, you might have a very even structure. Who knows? So why who knows? Because you have to, while you're designing your piece, pick in the right material based on the media that you're exposing your material to. You have to determine these kind of, you have to think about this kind of thing and determine the conditions for it, right? But if you don't know the thermal properties, you cannot possibly design or predetermine these conditions. These railways, for example, In the hot summer days, these railways expand, and in the cold winter days, they shrink. So you have to space them while you design the railway tracks at a certain distance, or while you're producing these railways from the factory. You have to think about these concerns as well, especially think about the high-speed trains, for example, right? Or this thermostat. This thermostat is based on the principle of thermal expansion. You have a certain fluid that you want to measure the temperature of, and that temperature is conducted to the bimetal metal stripe piece that you created there. You specifically pick two metals like copper and iron in this example that has a large thermal expansion coefficient difference, and you bond them. Once you bond them, once they shrink, what's going to happen? The thermal expansion coefficient larger one will shrink more, so it's going to be rounded in a lot more. Or if it's heated up, thermal expansion coefficient larger one will be open up more, so it's going to be opening up more. So there's a deflection in the coil, this bimetal strip coil. That's deflection determines is corresponding to certain temperature range. So with the knob I can arrange what kind of deflection I need, in other words, what kind of temperature I need behind the scenes, right? And you can easily control the temperature. Okay, so there are some other stuff that they use in your daily life, maybe, like how does a popcorn pops, like certain popcorns pop better and the other ones don't, and you get frustrated, right? And we'll see why is it so. Or for example, to the oven, you don't put a regular glass, you don't put your regular drinking glass into the oven to cook something. You put in a boron added glass, which is borosilicate glass, right? So why is that so, right? Or when you're designing your pots and pans in your kitchen, you don't design your pots and pans with the handle that is made up of metals, right? You use polymers. Why? Okay, and these, other than these, are more sophisticated use to them. For example, if you want to design a shuttle, a space shuttle, especially when you're going through the atmosphere at a certain speed, there's a high friction in between your shuttle and the atmosphere, so that creates extremely high temperatures on the surface of your shuttle. What kind of material you should pick that, so that, and how thick it should be, and at that temperature, while it's protecting your system, does it expand a lot more or less? If so, how big of a pieces that you get together, like these silica tiles here, or how big of a silica tile you can produce, right? So you have to think about a lot of things when you're producing these kind of systems. It's not only the thermal protection itself, but also, for example, if you're thinking about a chip design, you think about the thermal properties, just like in the hemp example. How can you remove the heat from the system? And also, how effectively you can operate your semiconductor, which is what? Electrical properties. If the semiconductor was giving off light at the same time, optoelectronic properties, right? So learn these properties each one by one, and then you might have to combine them in certain applications later in the upcoming sections, in your upcoming sections of your life. Okay, so in the scope of this chapter, the thermal properties, we'll see the certain terminology and how they change and why they change. We'll discuss heat capacity, specific heat, we'll define them. We'll define what the thermal energy is. We'll define a thermal expansion coefficient. What is a thermal expansion? We'll define a thermal conductivity, thermal stresses, and finally we'll define thermal shock resistance and wrap it up. This chapter is relatively a shorter chapter. Let's start it off. Heat capacity. The definition of heat capacity is the ability of a material to absorb heat to raise the temperature of the system 1 degree. So as you can see from this equation here, to raise this temperature 1 degree, 1 unit, how much heat you should supply to the system gives me the heat capacity of the system. So this heat capacity can be defined by two different ways, one of which is the at constant pressure and changing volume, or at constant volume and changing pressure. So heat capacity at constant pressure is designated as Cp, and heat capacity at constant volume is designated as Cv value. Well, we already defined it here. All these words we already said it in the previous slide, but the unit for the heat capacity is joules per mole Kelvin, or calories per mole Kelvin, right? Energy per mole Kelvin. But there is another quantity that we can define that's not per mole, that is per kilogram or grams. That is called the heat capacity per unit weight. The moles converted into weight, and that is called a specific heat. Where do I use specific heat? Well, if I have certain material, a mass that I know a weight of, then it might become handy, right? Excuse me. So if I'm describing a heat capacity raised in the temperature of the system, the amount of thermal energy I should supply, what is the thermal energy then? The thermal energy, the kinetic energy of the atomic motions and the potential energy of distortion of interatomic bonds. Of course, this is a more general expression, like kinetic energy of atomic motions means in the liquid or in the gaseous form, right? But for the solid form, that's more determined by these potential energy of distortion in between the atoms, atomic bonds. In other words, these atomic lattice vibrations, right? These lattice vibrations we defined coming from the gas, liquid, and the solid. In the solid, they attract and repel, and they form these bonds, but they don't stay at those equilibrium interatomic spacing positions strictly. At that high temperatures, right after you solidified it, maybe they are just still oscillating at a certain frequency and a range, and then as you lower the energy of the system, what's going to happen? They're going to oscillate less, and they're going to find that specific interatomic spacing, that lattice point, that maintains that lowest energy point. It's absolute zero, where you assume that there's no more lattice vibrations and the thermal energy is minimum, and so on. But anyhow, coming from the absolute zero, as I raise the temperature of the system, so the thermal energy of the system increase, because the lattice vibrations are increasing as I ever increase the temperature of the system. So these the vibration of these atoms create these elastic acoustic waves, that what we call phonons. As I increase the temperature of the system, of course, changes the wavelength of it. This is a very good explanation of what how a phonon looks like. These orange positions are the original atomic positions in the lattice, and blue ones are the displaced because of these vibrations. So these vibrations at high temperatures are displaced more. So you're creating these, you can see the creation of the lattice vibration. If it's like a subtle change, then you have a smaller wave. Then what do you have? As you increase the temperature, you have higher vibrational displacement, and it creates a larger phonon, lattice vibration waves, which we call the phonons, right? And that determines the thermal energy of the system. So with the increase in temperature, how does the heat capacity change? So increase in temperature means how much unit thermal energy you give to increase the temperature of the system, or how much unit energy is needed, right? So that ratio we define as the heat capacity comes to a point, merges to a point where the amount of energy that is needed to change and raise the temperature of the system gets constant after a while. In early 1800s, the French scientists Dulong and Petit, they conducted an experiment on different elements to find the molar heat capacity of these elements, and they found that the molar heat capacity do not change much. It's in the range of 22.5 to 30. At those times, they didn't know what the gas constant is, but they concluded that the heat capacity of elements do not change, and they are all pretty much in the range of 22.5 to 30. Okay, but it turns out to be later in later years, the gas constant, which is 8.31, 3 times gas constant, which is around 25, right, corresponds to that heat capacity value in each element merges into. So, but the temperature at which that element merges into is different, right? So, if you look at the classical Dulong-Petit law, which is this law, they claim that at any temperature this does not change. It merges around 25 in average for any element. But later, 100 years later, first Einstein and later following Einstein, Debye, created a model very similar to the electrons movements and the energy levels of those electrons in the material. Those derivations we've done in the electrical properties section, those density of states and Fermi direct distribution, very similar to those derivations. Debye treated phonons, these lattice, the phonons resulted from the lattice vibrations, these waves, in a box confined in dimension L, L, L in 3 dimension. Einstein, on the other hand, treated each element separately, each element's harmonic oscillation separately, while Debye treated these oscillations in the system as a collective oscillation. Their models are very similar to each other. I don't know if I ever put that anywhere, but if this is the Debye model, the Einstein's model goes very close to it, like maybe a little lower estimation. But anyhow, up to a certain temperature, which is called the Debye temperature, the heat capacity increases. The heat capacity increased and merges into the certain value, which is around 25. But this heat capacity value increase with a certain constant A and times the temperature's third coefficient. So if you look at these different elements here, lead, copper, and silicon, for example, they all merge to a certain value, which is 25, but the coefficient of which they reach to that value is different for each one of them. So if you look at the Cp values, which is the heat capacity value at constant pressure, so as opposed to the Cv values that we're talking about here. Cv is the heat capacity at constant volume with change in pressure. But usually for solid materials at room temperature and below, the Cp and Cv values are very similar to each other, while the Cp value, which is the heat capacity at constant pressure, is almost always larger than the heat capacity value at constant volume. But if you compare the Cp values, the polymer's Cp value is much larger than the ceramics and metals. And why is that so? The reason for that is it goes back to the two things. One, the way the polymers bonded. Let's remember what was the polymer. A polymer is carbon-based backbone material, right? That is combined with chlorines, fluorines, like hydrogen and these A metals and so on, right? The carbon backbone. And that carbon backbone chains are, that carbon backbone is bonded with the covalent bonding, but those carbon backbones bonded with the secondary bonds in a traditional polymer, right? So because of this reason, first of all, because of these weak secondary interactions between those bonds, as you increase the temperature of the system, right? This is not Cv, this is Cp, as they increase the temperature of the system, what happens? First of all, these secondary bonds breaks and the system spends that thermal energy in expansion. So, and after which, because of the covalent bonding character in between these carbon backchain atoms, there's not much of an electron exchange in between them. So as you increase the temperature, the heat, you need to give higher thermal energy to raise the temperature of the system because of the lack of the electron exchange immobility. There are two reasons for it. Okay. So let's talk about thermal expansion coefficient. What is a thermal expansion coefficient? The origin for the thermal expansion coefficient comes from, again, bonding, chapter 2. It's very important. So what kind of graphs that we're looking at? We're looking at graphics, the overall energy graphics with respect to the interatomic distance. Let's remember from our original slide. We had two atoms. This is the interatomic spacing. And if they're infinitely separated, we are in this axis in infinity, right? And as they come together, how they come together, I lower the thermal energy of the system and they start to attract each other. We recovered this many times in different properties as well. Recently was in electrical properties. So these guys start to attract each other, right? And then what happens? They say, "Whoa, stop!" And I have electrons, you have electrons, and then just back away. And I need that personal distance, right? So that attractive and repulsive forces on the system creates an equilibrium interatomic distance in between them. And because of those repulsive and attractive forces, we can also define the energies in between these atoms when they form this bond. And right at where these forces are equal to 0, which is the derivation or the slope of the energy of the system is 0, which is the energy minima here, where my force is 0, which is the slope is the 0, right? Is composed of this energy diagram is also composed of what? Repulsive and attractive energies. Let's go back to our thermal expansion discussion. So I have a certain elements, two elements come together and they form a bond. But if somehow the repulsive and attractive energies, in other words, forces in between them, are different shaped. For example, if for the second system, for example, if I want to have such a deep energy and also a symmetric overall energy, what kind of relative repulsive and attractive forces curves should I have? I should have an attractive energy that starts at a much smaller interatomic distances and much steeper maybe, right? On the other hand, to have such an asymmetric overall energy curve, what kind of attractive and repulsive forces or energies should I have? I should start to have the attractive forces or energies way further apart of these elements, and they attract more as they get together. So, and all of a sudden there is a repulsive force or energy gets into play. So this kind of behavior will most likely create this asymmetric overall energy curve. So why do I care if it's asymmetric, if it's deep, or if it's symmetric? Well, I remember talking about it in class, but that directly relates to the thermal expansion. Because what thermal expansion is this? This is what's happening in between two atoms. But when I'm talking about a material, I'm talking about multiple atoms, many atoms, right? So think about this energy minima here. Let's say I'm at absolute 0 Kelvin, and then I'm raising the temperature of the system. As I raise the temperature, what's going to happen? For example, in this curve, let's talk about the symmetric curve. As I increase the temperature, if this is the interatomic distance, strictly, as I raise the temperature, let's say I went to T1, T2, T3, T4, the higher temperatures, I'm raising the thermal energy of the system. The interatomic distance position, which means the distance between these two atoms, once they start to oscillate, shrinks increase, shrinks, increase. So this curve represents at that temperature level what is the average distance in between them. I increase the temperature, it gets closer, further away, closer, further away, but the range at which this oscillates increase as I increase the temperature. So for a symmetric curve, if you look at overall, two atoms, while they're getting this much closer, the other two atoms are further apart this much further. So if you think about three atom system, let's say first atom and two atoms are closer this much, but the second and the third atom further away this much. So this cancels each other, creating this overall interatomic spacing, which does not change the overall volume of the system much. So for a system like the symmetric curve, I don't expect much of a thermal expansion. But let's take this case, for example. If I'm having this asymmetrical case, and if I raise the temperature of the system, the position of the interatomic distance is changing, skewed a little bit because of the favored attractive forces, right? So as I increase the, starting from the absolute zero, raise the temperature, and this oscillation starts, two atoms, atom 1 and atom 2, while they're getting closer this much, let's take this temperature, while they're getting this much closer, the atom 2 and 3 gets separated from each other, but not as much as 1 and 2 atoms getting closer. So in overall, if you look at the atom, you have a certain expansion in the material. So if you have, if you treat the system overall, not only two atoms, what are they doing, but like an overall an average, what like many multiple atoms are doing with this within the given range. In this range, they are symmetric around a certain value, but in this range, they're not symmetric around it. So therefore, there's always a net displacement in the overall size of the material, which creates this thermal expansion. Okay, so we already talked about this. If you want to define how much the material change and what is the we want to quantify what is the thermal expansion coefficient. It's a coefficient, right? So the change in the length should be related with the temperature, right? This equation does that. The final temperature I get to minus the initial temperature multiplied with that delta T, multiplied with certain coefficient, which is we call the thermal expansion coefficient, should be equal to the change in the elongation of the piece, which is the change in the length, percentage change in the length of the system, which we already defined as strain, if you remember, in the mechanical properties, which was the final length at the final temperature minus the initial length at the initial temperature over the initial length at initial temperature. That ratio, delta L over L initial, should be equal to some coefficient, which we call the thermal expansion coefficient, times the T final minus T initial, which is the delta T. All right. So this is the summary of the thermal expansion coefficient. It does not only occur in one dimension, it can happen in 3 dimensions. So if you want to define that in 3 dimensions, we have to take a ratio of change in volume over the initial volume, which is equal to not the linear expansion coefficient in 1 dimension, but this time volumetric thermal expansion coefficient times the delta T. That's that simple, okay? So how does the thermal expansion coefficient for different materials change? Of course, the polymers will have much larger the thermal expansion coefficient. Of course, because of the bond energies, their bond energy is much lower, and they have a lot more like asymmetric because of the secondary interactions as well. Of course, after which the metals come, because metallic bonds are less strong than the ionic bonds in the ceramic structures. So deeper this well here that we're talking about, of course, deeper this bond energy, less of a thermal expansion we can talk about. Here is the concept question. The question is asking, explain why a brass lid ring on a glass canning jar will loosen when heated. So you have a glass can and you have a brass lid. And if you heat it up, like you use it at home, like, you know, any of the jars, that if it's stuck, what do? You heat it up and it opens easily. Why? Because the thermal expansion of the glass is less than the thermal expansion coefficient of brass. Let's compare them. I believe the brass coefficient is very close to aluminum. This aluminum coefficient is around 23.6, and let's take a look at the soda lime glass. This is 9. So while the soda lime glass 9 units expanding, the aluminum is expanding, or brass, 23 units. So at any given higher temperatures, it expands more, so it opens the lid easier. The second part of the question is asking, suppose the ring is made of tungsten instead of brass. What will be the effect of heating the lid and jar? Not a good idea. The reason is right here. Look at tungsten. Tungsten's thermal expansion coefficient is 4.5 times 10 to the minus 6 per Kelvin, while that is for soda lime glass, it's 9. If I was to make a lid made up of tungsten in a regular soda lime glass bottle, then if I heat it up, what's going to happen? The glass will expand even more than tungsten, 2 times as much. Then it's going to be even harder to open the lid, right? Let's take a look at another thermal property, which is the thermal conductivity. When we talk about the thermal conductivity, of course, conductivity is a mechanism by which the thermal energy is transferred. How the thermal energy is transferred from high temperature to low temperature. If you don't have a thermal temperature difference at a certain environment, if the temperatures are equal, then there is no heat flux. The heat, the thermal energy is not transferred because the temperatures are equal. There's no reason for the heat to travel, okay? So the temperatures are the same. So if there is no need for the thermal energy or the heat to travel, then we don't care what the thermal conductivity is. But in this, specifically for the heat transport to occur, either by conductivity or convection or radiation, doesn't matter what kind of mechanism we're talking about, there's got to be a temperature difference. But in specific to our materials, we're not going to be talking about radiation, heat exchange, or convection thermal transport, but conductivity. Why? Because we're talking about a solid system. If we were talking about a liquid or gas system, then we would be talking about convection, right? So in the solid system, the main thermal property, one of the main thermal property, is the thermal conductivity of the system. And that is again determined by what kind of bond this system makes. In other words, how free these electrons are in the valences. So first of all, if I have a piece that has a certain temperature difference, as we said, there's a heat flux. If these temperatures are constant, they don't change, I have a steady state heat flux. If these temperatures are changing in time, then I have an unsteady state heat flux. So for the system always, if this is higher temperature, this is lower temperature, it tries to equilibrate the temperatures, the thermal energies of the system, and to equilibrate that, there is a heat flux, right? But how fast this heat is traveled depends on a certain coefficient that we call thermal conductivity. The thermal conductivity for metals, ceramics, and polymers will be different because the mechanism of heat transfer is different in those 3 materials. Hold on, I'm back. So when we talk about the heat flux, higher the temperature difference in between those 2 endpoints, I have a higher heat flux per meter square per second. It's a rate at which the thermal energy is transported. Longer it is, the distance between the temperatures T2 and T1, of course, lower the heat flux. Shorter it is, faster it is, of course. And also, there is a material property that we call the thermal conductivity. Like, no matter how high the temperature difference is, how short is the distance, if I have an extremely low thermal conductivity material, insulating material in other words, then heat flux will be low. But so this temperature and the X value is a geometric value. Temperature is something external that I can play with. But when we talk about a material property, this thermal conductivity is important, which is also a function of temperature. We'll see. But what composes the thermal conductivity? By the way, this is the Fourier's law. It says it's a fixed first law of atomic motion. Is very similar to that in the diffusion mechanisms, or for a steady state heat conduction, and also for non-steady state there is a second order heat transport. Anyhow, this K value here, which is the coefficient of thermal conduction, composed of two main components. One of them is based on the phonons, lattice vibrations, which is represented as KL, I believe here, and this KE is the electrons. So the reason, or how fast the material conducts this heat, mainly based on this material's free electrons, and also, except for electrons, the lattice vibrations. So the lattice vibrations, along with the mobile electrons, create total ability of the system to conduct. Therefore, for metals especially, we can directly relate the electrical conductivity, which is a sigma, to the thermal conductivity, which is K. If you look at it, K is equal to thermal conductivity times a length, not a length, L, which is a constant for a different material, times the temperature. So, for example, for an aluminum, and a conductivity for a certain aluminum piece, if you multiply this L coefficient with the conductivity of the aluminum, what do I get? I get a K thermal conductivity equation based on the temperature. This is for metals. But on the other hand, for ceramics and polymers, think about the metals. Metals are the sea of electrons, right? In the thermal conductivity equation, which term dominates here? Of course, I'm going to copy this to the other page. Of course, this electrons conductivity term, it dominates the conductivity due to the lattice vibrations, which is the phonons. If you look at this, I'm going to copy that here, make it a little smaller. So if you look at the metals, all these numbers being high is because of this K value, because of this electrons movement in the material, carrying that thermal energy easily within that sea of electrons from one end to another end where the temperature difference exists, right? So that's why metals have very high thermal conductivity values. But on the other hand, ceramics and polymers, of course, if you did not create a conducting polymer or ceramic with doping and so on, I'm talking about as is, innate ceramics and polymer, this electron contribution to the conductivity is extremely weak. We are mostly dominated with phonon energy transfer. So this vibration of atoms around the lattice points is the most predominant mechanism for ceramics. On the other hand, for polymers, this is mostly done by these vibrations, but on top of that, the rotation of chain and molecules also contribute to the electrical conductivity. The material structure plays an important role too. For example, for metals, if in a copper and zinc alloy, copper has a certain conductivity and it's known to be noble metal, right? Copper, silver, and gold, because of their outermost shell, 1s half-filled shells, right? They are good, very good conductors. So, but as I add zinc, for example, into copper, what am I creating? I'm creating scattering sites for these electrons, so that it's a worse of a conductor, electrical conductor, as well as a thermal conductor. So if you want to determine if a metal is a good thermal conductor or not, please take a look at its electrical conductivity value, because the thermal conductivity is mainly governed by the the electrons, the free carriers in the material. On the other hand, for ceramics, since we're talking about the phonon vibrations, these phonon vibrations, of course, we will have less of a thermal conductivity as we increase the temperature. But as we increase temperature ever more, then we will be creating again a scattering factor in the ceramic material. So these two phenomena, I'm gonna just generalize for ceramics, but that popcorn example I'd like to really give here. As a general rule, if you would like to lower the K value more, you have to create amorphous ceramic as opposed to crystalline ceramic. Why? Because it creates more scattering centers for phonons. The thermal conductivity of the ceramics can be decreased even more. Instead of having a dense ceramic, if you create porosity in it, again you lower the overall K value of the ceramic thermal conductivity. Okay. So similarly for polymers, increasing crystallinity increases the thermal conductivity, just like ceramics or metals as well. But I'd like to talk about this corn kernel. I don't know if you see the picture here, but most probably in your slides you're going to be seeing that. The corn kernel is each piece of those corns that you pop made up of a hull, like outside shell, and an inner core. The outer core hull seals the inside, of course, the inner content, and this outside hull is moisture sealed, and inside of it, it's very hard. Outer of it, you know that, of course, and inside of it, very soft, very moist content in it. When I put it under the heat, as it gets the thermal energy, the moisture content inside wants to it creates a certain pressure inside, and then if this outer hull is strong enough, it will keep it contained inside, and as it cracks open, then it will pop. Then we call this it popped. But and this is done by a cellulose that covers the if you cover the hull with the cellulose, then those cellulose are very hard and a very good conducting, high conductivity, but at the same time very hard material that creates that atmosphere inside to allow the inner moisture to build up enough pressure to create that popping effect. But if you don't have that cellulose, the sufficient cellulose surrounding the hull, then you will have those less conducting and less resistant outer hull, which doesn't allow this popping process. Okay, let's go through some concept check questions. We are almost done with the chapter, but we have maybe 10 or 15 minutes more to go. But let's answer some concept check questions. First concept check question. The thermal conductivity of a plain carbon steel is greater than for a stainless steel. Why is so? Well, of course, what is the main difference between a plain carbon steel and a stainless steel? Carbon content. The more carbon content you have, they're what? Both metals. So the thermal conductivity for metals is governed by what? Electron mobility. If you put more carbon in it, do you have more scattering centers for electrons or less? Of course more. So what happens to thermal conductivity? Goes down, right? Okay. Concept checked question, second one. The thermal conductivity of a single crystal ceramic specimen is slightly greater than the polycrystalline one of the same material. Why is it so? Well, again, it comes to the scattering, right? But this time it's not the electrons. The thermal conductivity of ceramics is dominated by what? Lattice vibrations. So for a single crystal versus polycrystal, what is the difference? Interfaces, grain boundaries. So you have more scattering centers for those lattice vibrations, which carries this thermal energy from point A to point B. Let's check the last question. Explain why on a cold day the metal door handle of an automobile feels colder to the touch than a plastic steering wheel. Well, even though both are at the same temperature. So we all experience that. Of course, if you're not living in Hawaii or Florida or maybe in California. So if you go to your car, if you just open the door handle, then what do you feel? You feel much colder. But although everywhere is isothermal, right? Outside temperature is -5 degrees, let's say. Everything you touch, the tree, which sufficiently stayed at that temperature, will be -5 degrees, right? It's isothermal everywhere. So open the door and then you get in the car and you touch the steering wheel. Well, the outside that, the handle, it almost sticks to your skin. It's so cold, but as opposed to the steering wheel. Why? Well, it has to do with the thermal conductivity. Even though you have the same temperature difference, like let's take a look at here, this story here. T2 is my hand. It's what the body temperature. And what is a T1? T1 is the -5 outside temperature. It's isothermal everywhere. For the door handle, what do I have? Let's say dx is the same in both because I'm touching it. I have the same distance in between my hand and the wheel or the handle. What is different here? This K value. If this K value is large, like metal, what's going to happen? It's going to suck out the energy from my body to the handle a lot more. So I'm going to feel it colder, right? Because it's sucking out my energy faster. But on the other hand, for a polymer, since this K is much lower, what am I going to feel? I'm not going to feel as much sucked out. So that's why it's not going to feel as cold. Okay. Let's talk about thermal stresses. Well, the thermal stresses can occur for multiple reasons. One of them is if I have a certain, let's say, a length material and I already fixed it as a design, like this pen, for example, and this system is raised to a certain temperature. But the size of the system is kept the same. So as the temperature is raised, what's going to happen? This pen would like to increase its size because of thermal expansion. Because of the thermal expansion, it want to increase its size, but it will not be able to. So what kind of mechanical stress due to thermal energy it creates on the pencil is somehow a compressive stress, right? Because it wants to expand, but it keeps the same, so there's compressive stress on it. Or if I was applying a tensile strain and cool it, it would be the opposite effect. And there is a little example problem here. Let's say we have a brass rod, which is stress-free at room temperature. And we raise the temperature of the brass rod to a certain temperature. And the question is asking, at what temperature does the stress, the compressive stress, reaches to 172 megapascal? Okay, so we have a certain stress, which is stress is given as the, if you remember from the mechanical properties section, is equal to the Young's modulus times the strain in the material. So, but this Young's modulus times the strain value is already given as 172 megapascal. If I know the Young's modulus and divide the stress value into the Young's modulus, what do I get? I get the strain, which is delta L over L, which is the change in length, will be equal to thermal expansion coefficient times the change in temperature, which we already seen in thermal expansion coefficient, right? So from stress value, I can get by dividing into the Young's modulus of the brass rod, which will be equal to the strain value, and that strain value is equal to thermal expansion coefficient times the temperature difference. So I know I can get the brass thermal expansion coefficient, which is 20 times 10 to the minus 6 per degree C, and the temperature at which the stress is exposed is asked, that T minus the T room, which is 20 degrees C. Young's modulus value for brass, we can look it up, that's a material quantity as well, which is 100 gigapascal. And if we know the total stress on the brass rod, which is 172 megapascal, minus because it's compressive, then what do I obtain? Plug and play, 106 degrees C as the temperature at which, if you want to confine the shape of that brass rod, the stress it experiences is 172 megapascal. The temperature is 106 degrees C. Perfecto. So this is the thermal stress. Well, that stress over the Young's modulus value is equal to strain, which we already seen in thermal expansion as delta L over L0, right? So let's take a look at another example. No, this is the same example, by the way. This example problem in the book is already been solved here. You can also see, which is 19.1 in your book. Right. We can also create stresses in the material based on the dimensions that we pick, and based on like geometry, the design that we have, and based on the conditions that we expose, the thermal conditions that we expose that geometric piece to. What kind of environmental conditions that we're exposing to, right? So this is a very common example. We did not have a chance to see that. I think this was, which chapter was that? I don't remember. Might be in chapter 8. I don't remember. But what's really happening here is I have a certain 1040 steel and 4140 steel. These two steels have to, like, this is the diameter, this from here to here. This is radius. This is the total diameter of the system. So I'm giving to the rod, two different material rods, water spray at 24 degrees C from the bottom. What really is this cylindrical specimen is experiencing is, on the outside, it is experiencing whatever is the water temperature, is 24 degrees C in the outside, but this is the hardness value, by the way, it's not the temperature gradient, but on the outside, it is experiencing that temperature. Let's say I took it out at 400 degrees C from the oven, and delta T in the outside being 400 minus 24 sharp. But as you go toward the inner, the temperature is not constant. There is a temperature gradient to inside. As the temperature is much higher inside and experienced temperature is much higher, delta T is much lower, then in the center I'm going to have larger microstructure, larger grains, and the outside I'm going to have smaller grains. So from in and out, I created a different hardness microstructure profile and hardness profile. This kind of created stress in the material, but this kind of stress for a ductile material I would prefer. Of course, this is a design experiment, the previous example that we gave. Of course, these two different materials having a different thermal conductivities have a different temperature profiles, right? But anyhow, this is a very common example, you probably know, tempered glass that you use in your houses or like on the screen, the computer screen, to prevent that breakage. How do you obtain a tempered glass? You take a piece of regular glass and you put your glass at 600 degrees Celsius to the oven, and around 600, 620 in industry. And so you homogenize your glass and you take it out. As soon as you take it out, you blow air on it, just like that water blowing in that test that in the previous slide. So at room temperature air blown, outside, depending on the thickness of the glass, of course, in the outer thicknesses of the glass, which is almost a 0.21 T thickness of the total thickness, will cool faster. And inside of that, in inner and outer, you're blowing air from both sides of the glass. So you create that cool faster. You already frozen the structure there, and inside is still trying to cool, right? So inside of the structure, in that case, is under tension, and outside is under compression. So because of these compressive and tensile stresses created in throughout the thickness of the glass, if I drop the glass on the floor, these compressive stresses, unless I get over those compressive stresses, I will not be able to break the glass. Okay, that's the idea of the tempered glass. And then we intentionally introduce these thermal stresses. The thermal shock resistance for the brittle materials is much larger. In other words, if a material is brittle, like ceramics, for example, these changes in the temperatures, like sudden changes in the temperatures, is to the sudden changes in the temperatures, the material is less resistant. But we can always improve upon these thermal shocks. And in this slide, that's what we're going to discuss. So we have, let's say, a material that was initially at T1 temperature and rapidly cooled to T2. On the surface of it, that's T2 temperature is experienced, and inside it's still at T1. So the tension, just like we talked about the fixated sample stress exposure or the thermal expansion coefficient section, it's the same idea. The quench rate, the tension developed at the interface right here, is the stress that stress that the material is exposed to, is equal to the Young's modulus times the thermal expansion coefficient, but going from T1 initial temperature to that sudden degrees T2 temperature. So that T1 minus T2 is critical to create a fracture. How do you calculate the critical temperature difference, that T1 minus T2 that creates a fracture? Hold on, which I already do, but I think there's something wrong with it. But anyhow, so that this max temperature difference that creates the fracture can be calculated with this fracture strength over the Young's modulus times the thermal expansion coefficient. So the only way to actually increase the thermal shock resistance of the material by creating a very large value of this ratio, so that you can obtain a larger temperature difference and still nothing happens to the material, is by reducing the thermal expansion coefficient. So the addition of a boron into the material is doing this magic, where it's reducing the thermal expansion coefficient of the glass. Well, that concludes our thermal properties section. We all seen these topics here, and also while we're discussing each of these topics, I try to mention some application areas. I hope you enjoyed it. I'll get to see you in magnetic properties lecture series in the upcoming days. Thanks for listening.